Hi, so I'm Carleton Coffrin, a scientist at Los Alamos National Lab. And one of the questions that has mesmerized me for the past 5 to 10 years has been seeking what I might call the holy grail of optimization on a quantum annealer. And that is essentially a very easy turnkey solution to optimization. You want to send the hardware an Ising model and get back a near optimal solution much, much faster than any other solution method out there. If that happens, then you've got a really transformational technology for your applications. Now, there's a lot of details, like technical details, to specifying what the Holy Grail is and how you measure and show that kind of a statement. You have to make a clear definition of what is meant by near optimal, what any other solution methods are you going to consider, and what it really means to be much, much faster. So in this talk, I'm going to show you an example of how we're thinking about that at Los Alamos and my team, and some really exciting performance benchmarking results on the latest Advantage system. Now, I will warn you, seeking the Holy Grail is not for the weak of heart. This is an incredibly challenging task. And part of it is because the D-Wave platform has a number of constraints on it that you have to keep in mind. So first one is that the size of problems you can fit on the current generation is about medium size by optimization standards. That's 5,000 decision variables. The graph that is implemented on the hardware, which is currently the Pegasus architecture I've shown you here, is a relatively sparse graph by optimization standards. You also have a fixed energy scale, so essentially an effective temperature on the machine. There's flux qubit noise. So all of these different constraints play into the difficulty of encoding hard problems and then measuring their performance. Now, I think it's important to acknowledge that benchmarking optimization is a really, really high bar to set. There are great results from D-Wave. You saw some of them yesterday in doing quantum simulation really, really fast. So here is a high-profile paper written by Andrew King and others showing that for certain types of quantum simulation, the hardware platform is about 10 to the 6 times faster than the next best classical option. And that's fantastic. But when you look at optimization-based performance measures, you're setting a much higher bar. Part of the reason for that is that you're looking for one best solution, where this hardware platform does a great job at producing 10,000 really, really good solutions. And so you're looking for an individual solution and not like a distribution of states. So that's a really big difference than a quantum simulation task. Now, I'll note an open research topic in optimization is how can you use that huge family of 1,000 or 10,000 solutions to accelerate optimization. We saw things like the portfolio optimization example earlier. But in this talk, I'm going to ignore that, and I'm going to do a super classic type of optimization benchmarking study where we're looking for one best solution. Now, what I'm going to tell you about is what we're calling corrupted bias ferromagnets. This is a new class or characterization of Ising models, which we've designed over many years of testing, specifically for benchmarking D-Wave hardware. This is not the holy grail I described to you. We're still seeking that. But it is exciting. And so the talk punchline, why you should really pay attention, is that I'll show that the Advantage 4.1 system, compared to state-of-the-art alternatives, we're seeing can be up to 50 times faster in raw wall clock runtime under ideal communication settings, and is still 15 times faster if we use the cloud computing overhead. So that's like the real user experience we experience at Los Alamos sending work out to Burnaby. So let me tell you now a bit about our approach to benchmarking. The computational task we're going to consider is minimization of the Ising model. So we're just looking for the lowest energy solutions to this particular quadratic function over -1 and 1 variables. This is an NP-hard problem in general, so we can presumably encode very challenging problems. We're only going to consider what we call hardware-native D-Wave instances. So we're going to build these Ising problems so they match exactly the hardware graph that's in the Advantage 1 system. So it follows this Pegasus 16 graph structure. And then the parameters j and h in this function are between -1 and 1 and -4 and 4 to match exactly what the hardware supports. Now, I would like to mention, when it comes to solving real applications on a D-Wave system, You actually have a whole stack of computations you're going to do. You're going to start with maybe a Cubo version of your problem. Then you're going to translate into an Ising model. Then you may have to do a hardware embedding, which involves putting in chains and rescaling the whole energy function. And then you send it off to the D-Wave hardware. And then after that, you resolve broken chains, and you get your Cubo solutions. Now, at each one of these layers, you can run into difficulties in performance, in terms of coefficient ranges or blow up of the number of variables you need. And one limitation of what I'm going to show you today is that I'm only focusing on this one little piece of the stack, the D-Wave hardware performance. And I'm asking the question, is the D-Wave computer the best solver in the world for solving these hardware native problems? As you go to more practical problems, you have to consider the full stack. So this is the general approach, like how do you build and study hardware native problems? We begin with the D-Wave hardware graph. I'm showing you an older generation C16 here on the left. And then you have a collection of interesting classical solvers you would like to compare to. Gurobi is a commercial optimization solver. You can develop greedy algorithms, simulated annealing. There's a whole family of these things. So we take the hardware graph, and then we apply a problem generation algorithm. OK, there we go. Problem generation algorithm, which will look at the hardware graph and the chip properties, and then make a hopefully interesting optimization problem. This blue and red image is the generated optimization problem. Now, we can take that optimization problem, minimize the Ising model, and send it to all of these interesting competitive solvers, but also send it back to the D-Wave hardware and solve it there. Now, the key here, and the whole reason that we're doing this procedure, is because we built the instance to exactly match the hardware platform. We don't need to do embedding. It's kind of like a hardware native. We don't need to think about the complications of all those other steps in the stack. Now, you don't want to do this just once. Showing that you can solve one optimization problem really fast is not really great benchmarking. So we're going to generate hundreds of these randomly generated instances and benchmark a family of them and see how everybody does. The key metric that we use to study this is what I would call a performance profile metric or a runtime profile. And you're going to see, this is the only type of figure I'm going to show you, so let's take the time to understand the cartoon version now. On the x-axis, you have the runtime of the computation, which is in a log scale. This is a wall clock runtime. On the y-axis, you have the quality of the solution. So basically, what happens over time is every algorithm starts with some particular solution quality and slowly improves it over time. Eventually, you can get to what's called an optimal solution, the best possible solution. Sometimes on my graphs, there's a bar to indicate that. And then we can measure the relative gap from the best solution or the optimal solution to the other, the profile of the optimization method. So this is really cool because you can see the solution quality versus time, runtime trade-off. So this is the kind of result for performance profiling we were seeing back in 2017 when I started using the D-Wave quantum computer. We had a 2x machine at Los Alamos. So what you can see here is a comparison. We actually compared 6 algorithms in this particular case. The orange line is the best classical optimization method at that time. And then the green line is what we got out of this D-Wave 2x machine. What you see is that for very, very short time scales, both are very similar in solution quality. They're basically parallel. And then as you increase time, the classical algorithm was getting a better solution, while the quality of the D-Wave solution kind of got stuck at a particular level. Now, this was discouraging to many people using this platform at that point in time. But it wasn't discouraging to me. And the important point here is to understand this relative measure on the side. So the difference here is less than 1% in total solution quality. So from my perspective as a practitioner of optimization, these solutions are both very, very good. It's like kind of tossing a coin between two very good solutions. So I was like, well, what happens when the classical solvers don't do so well? And I've been continuing that study ever since. So over the past 5 years, since that first study I showed you, my group and I have been doing a variety of different research papers understanding where the hardware really succeeds, what are some of its weaknesses, how does it work on different types of problems. And what I'm going to show you now is kind of the fruits of all of that research over many years. So I'm going to show you optimization performance results for a couple of D-Wave systems, including the Advantage. So let's begin with the 2000Q system. At some point, Los Alamos upgraded from a 2X system to a 2000Q system. And in benchmarking that system, we came up with a particular type of problem, which we called that corrupted biased ferromagnet I told you about. So we're going to put in hardware-native Ising models like I showed you, but we generate random instances following the particular distribution that you see here. So it's like linear term is 0 with 97%, it's -1 with 2%, and +1 with 1%, and then you set the j's with a similar probability distribution. When you run that family of instances on the hardware, you see a figure like what you see on the right here. So on the left, you have the 2X results, and then on the right, you have the 2000Q results. Now, the first really good news is that the green line is lower in this graph. So that means the quality of solution coming out of the D-Wave hardware is consistently better than the best classical solution, which was in orange. So if we just like highlight some of the big differences in the 2X generation and the 2000Q generation, firstly, this optimization problem is much, much more difficult. And the reason is that you see the relative gap at low time was around 2.5%, where on the previous generation it was like 0.4%. So we actually have an interesting signal. Are you finding better solution optimization quality solutions? And the time to find a comparable solution at a given quality is actually much better for the quantum annealing hardware. So that's, if you take a slice across the x-axis, that's what you see there. So this was very encouraging. But I will note that there was a bit of an Achilles heel to this result, which maybe many people didn't appreciate, which is that the run times we're talking about here are 1 second and less. So it's like up to 1/100th of a second. So if you consider the amount of time it takes to call a remote cloud system and get your result back, that's on the order of like 1 to 5 seconds, just to transfer the data over the internet. So if you wanted to deploy this using like a cloud D-Wave computer, this runtime advantage would just disappear instantly. And you could make an argument that by putting your classical application like right next to the quantum annealer, it would have a benefit. But that's a really big investment to make for like less than 1 second runtime improvement. So I didn't say we could do it with cloud or anything like that in this paper. Now we're going to go through the results on the latest Advantage chip. This is really the key piece of this whole paper. Now the chip is much bigger. It's like it's 5,000 qubits instead of 2,000, and it has a much denser graph to build those challenging optimization problems. Because the graph changed, we had to change the CBFM distribution. That's that probability of how you set the H's and J's. We call it CBFMP for Pegasus topology. But it's still a very simple distribution, like I just wrote it on the slide for you there. If you dig into this paper, you're going to see that we threw a lot of different solvers at this problem. So we considered approximately 10 classical optimization solutions. We played with a few key parameters on the D-Wave platform, including like annealing time and other key features. So I won't go through all of them, but I will try to communicate to you the highlights of the most kind of significant families of algorithms. OK, so what are you seeing in this picture? The x-axis is runtime. It's in a log scale. The y-axis is relative solution quality, also in a log scale. The black line is the quality of solution you get outside from the Advantage 4.1 system on these particular instances. And then all the other colored lines are like different classical competitor solutions. So the first thing to note is that there are a number of classical solutions, like mixed integer programming. It's the blue line with Gurobi. You've got a greedy solution with the red line. Those ones never find a solution that's as good as what the D-Wave will output in any short anneal cycle. So like you could run it as fast as you want. You'll never, those classical methods will never get equal solution quality. I mean, not never, but I ran it for over an hour. So let's say within 2 hours, you'll never get anything of what you can get in like 1/100th of a second. Then you have some other methods like spin vector Monte Carlo, simulated annealing, parallel tempering with isometric cluster moves, which is broadly considered the best classical competitor for the D-Wave hardware. And those methods will find an equal quality solution, but it takes a significant time. Like you can see where they cross the dashed line is about at 100 seconds. Now, the thing that is really exciting for me, and I hope for you too, about this plot, is actually these open circles. So up until this point, I have only showed you the amount of QPU chip time you were using. So it's in the D-Wave API, this is called QPU access time, the amount you spend on their server. These open circles are the real wall clock time that you experience as a user sitting in Los Alamos, sending the job to Burnaby, getting the result back to you. And the really exciting thing is that they are down and to the left from all these classical methods. So that means as a user of the cloud service now, you can actually see a runtime performance gain, and that's the first time I have ever seen that before. Now, I'm going to show you another figure, but let me explain exactly what it is. An important critique of this particular solution method is that there appears to be, with the analysis I did, a quality limit you hit. It's about 0.5% of an optimality gap. And that's what's in this long dash line here. So if you ask the question, how long does it take for a quantum annealer to get below that threshold, it's going to be a huge number, like positive infinity. But if you can reasonably ask, how long would it take your classical solution to match that particular quality you can get with the quantum annealer? And that's what I'm going to show you is what's called a time to target metric. How much time does it take you to get to this particular target of solution? And I'm going to show you the relative ratio, runtime ratio of the quantum annealing time versus the next best algorithm. OK, so here's the figure. In the beginning of the talk, I promised you a 50x and 15x runtime improvement, and this is where I'm showing it to you. So what we're seeing is the runtime performance gain by when you run on the Advantage system compared to simulated annealing and this parallel tempering solver, which we compare their runtime to match the same solution quality. And on the x-axis, you see the size of the problem. So when you get up to the 5,500 qubit size problems, you can see that the parallel tempering solver is the best solver, but with no communication overheads, it takes 50 times longer to find an equal quality solution. And if you include those communication overheads, it takes 15 times longer. If you consider simulated annealing, which is another popular comparison point, it's even worse. But we won't talk about that because it's not state of the art. One thing I really loved about this result is that I had been worrying for myself as a scientist, could I have seen these amazing performance results on those 2000 Q machines that have been developed many years before? And I think the answer is no, because of this particular plot. If you look at the performance of the pink lines at the 2000 qubit scale, it was a very small margin of runtime improvement. And so even if we had run this whole experiment and we had a Pegasus chip with 2000 qubits, it still wouldn't have looked that exciting to see those runtime gains. But you can see as you get up into the 4,000 and 5,000 qubit range, it starts to get quite compelling. And you could imagine if you carry out those trend lines to the 7,000 qubit range, it gets quite compelling. So I believe, with big question marks, this is the first ever demonstration that a quantum computer is a state-of-the-art heuristic for combinatorial optimization. I personally don't know any other method that can do better than this quantum advantage system. But I say that with a big question mark because if you think otherwise, please come to me. I would love to talk about it. OK, so let me just wrap up. I want to emphasize, I mean, I'm really excited about these results. I think they're really interesting and exciting. But this is not what I would call an irrefutable performance demonstration of quantum annealing or this particular platform. So there's many things you could try to improve the classical or the alternate solution methods. You could bring massively parallel computations using high-performance computers to the table. You could try building specialized hardware for solving these types of optimization problems and then compare that. And then, of course, someone could always come up with a new brilliant algorithm, parallel tempering plus plus, that I haven't thought of, and it might dramatically change these results. But right now, based on the current understanding of all these fields, these results are looking really good. So I think these results are an encouraging sign, and that quantum annealing is really establishing its niche as in the portfolio of optimization solutions. I showed you that the runtime benefits occur at a particular quality threshold and at really fast runtimes, like less than 1 second runtimes. As soon as you have a bigger time budget, you have other methods at your disposal. I think that the Advantage 4.1 system sets a relatively high bar for optimization performance. And we've seen, as I showed you in all these results, like steady improvements over the years with each generation of quantum annealing device. So if that keeps up, things are going to be really exciting in the next couple of years. All right. Thank you very much.